Hello, my name is Isaimar, and I'm gonna talk about quicksort, the quicksort algorithm. It's commonly used for sorting arrays, and it's a step up from other algorithms like merge sort. In some examples of its real life uses is on computer graphics as image rendering or data visualizations, numerical computations, and matrix sorting. So this algorithm uses a technique called divide and conquer. And this technique means that it chooses um, one element in the list and then divides that list into two lists, and then those two lists into four lists, and so forth until it gets small enough that it can order those lists individually. And the reason why it's good is because it can order those lists individual at the same time. So that's why it's called divide and conquer. And also, it's going to be a recursive algorithm, which means that it's going to be calling itself. Um, it's going to be call itself in the first half of the list and in the second half of the list. And here is an explanation of how the algorithm works. We first choose the last item as the pivot. This is going to be the item that is going to be split in the list at the end. And then we're going to choose the first item as the LMGP, which means leftmost greater than the pivot. This is going to be the how we're going to know which one is going to be greater than the pivot. So after that, we're going to go through the list and we're going to compare the items to the pivot. We're going to have two cases. If it's greater than the pivot, we're going to do nothing and we're just going to move to the next item. If it's less or equal to the pivot, we're going to move the LNGP 1 to the right and then swap the LNGP with the current index item. And then we're going to return the pivot index. After that, we're going to do the same thing with the first half and the second half before and after the pivot. And at the end, we should have an ordered list. So let's go through an example. So here we have an unordered list of 1, 2, 3, 4, 5, 6 items, and we are gonna go through the loop together. So we have first the current index, which starts here, and then the LNGP, which both start at the beginning, and then we have the pivot as the 4. So now we're gonna loop through the list from left to right and compare the items of the pivot. So if it's greater, we're gonna look at 3 first, and since it's less or equal to the pivot, 3 is less than 4, we're gonna move the LNGP 1 to the right, and then swap the LNGP with this current index item. So in this case, it's only a 3 with 3, so the current index and the LNGP are the same, so when it swaps, it's gonna be still 3. After that, we're gonna look at the next item. It's gonna be 2. 2 is also less or equal to the pivot, so we move the LNGP 1 to the right, and then swap the index with the LNGP, which is gonna be the same. Then we're gonna look at the 5. And now, this one is gonna be greater than the pivot, so it's gonna be case A, which means we're gonna do nothing, and we're just gonna move to the next item. When we look at 1, it's less or equal to the pivot, so we're gonna move the LNGP 1 to the right, and then swap the LNGP with the current index, which in this case is going to be 5 with 1. So see how that's how we are going to organize the list. So now we're going to move to the next item. Number 6 is greater than the pivot, so we do nothing. And we move to the next item. It's going to be a 4. So now we're in the pivot, which means is equal to the pivot. So we move the LNGP 1 to the right, and then swap the LNGP with the current index, which in this case is going to be 5 with 4. And now the new LNGP is going to be, the pivot is now going to be here in this position. And this is how we're going to be able to divide the list and see how now every item at the left of the pivot is going to be less, and every item at the right is going to be more. So that way we're going to be able to organize this list individually by calling it the function in each of these lists. Now let's look at some code. Here we have a function called sort, where we give an input of a list called data, and then the first integer and the last integer in the list to know how big the list is. So our base case is going to be if the first index is equal or greater than the last, we're just going to stop, which means that we've gone through all the items in the list and we know that it's been sorted. After that, we're going to call the function called partition, which is what's going to give us the pivot and index to divide it in, and it's going to do the for loop there to order the list into the first half and the second half. And then when we have those we have the pivot index, we're going to call the same function sort to the first half of the list and then the second half of the list. Here's the function partition. We first choose the pivot as the last item, then LNGP as the first item, and then go through the loop. As a for loop, and we compare the pivot to the item that we're looking at. And here is if it's greater, we do nothing, and if it's less or equal to it, we add 1 to the LNGP and then swap the item, the LNGP with the current data that we're looking at. So we're going to do that for every item until we get to the end, and at the end we're going to swap the LNGP with the pivot. So we add 1 to the LNGP and then swap, and then we're going to return the new LNGP, which is just going to be the pivot, that index. We're going to want to know where it is, so we can call the function again. Now let's talk about performance. So when we look at performance in an algorithm, we talk about big O notation, which means how many operations it takes to how many elements the list has. So the more elements the list has is going to have to do more operations, which is going to increase the time of performance. And the performance for this algorithm is, as its worst case, it's O of n squared, and as its base case is O of n log n, which means, here's an example. If n is 1000, means that the list is 1000 items long. It's going to take 333 times slower for n squared than n log n to do the same, to sort the same algorithm, which makes sense since here we have n log n, and then here we have n squared right here. So it's a lot faster. All right, and now we're gonna look at some test case that I made for this algorithm. I made some test case to see a sorted list, then a reverse sorted list, just to test all the um, possible cases. Also, a list with only one item, or even an empty list, and we're going to see if it passes. And yep, all the test cases were passed successfully. So yeah, and that is all. So thank you for watching.